All right, I'm back. I wanted to just take a moment to interrupt things so that you can have a nice stopping point. Okay, so I was just saying that one of the biggest components of or one of the biggest agents in hemoglobin and myoglobin's different binding curves was their structures. Hemoglobin and myoglobin are considerably different in structure, not what those structures are based on. Because if you remember, both hemoglobin and myoglobin were comprised of something known as a globin fold. So they had similar properties, they have very similar shapes and structures, but they're going to vary a little bit. And oxygen, by having four subunits, it's like in a different game. Hemoglobin has two different states, two stable states. Those states are known as the T state and the R state. Now, oxygen can bind to both of those, but has a considerably higher affinity for the R state. Okay. In the absence of oxygen, the T state predominates. So you can kind of think about it as the T state is your deoxyhemoglobin. The R state is your oxygenated hemoglobin. And what you're seeing here, where I've just drawn a little something of a star, is you're seeing these kind of shared residues or common residues just to illustrate how these proteins have changed. So let me go ahead and let's see if can I edit this and tinker with the, you know what I'm going to do? Crop this. What I want to do is I want to make this first. I'm going to pause my recording. All right, I'm back. What I wanted to do was give you to take this image on the right hand side where we've got our deoxygenated hemoglobin and our oxygenated hemoglobin. And I wanted to use this oxygenated hemoglobin, the deoxygenated hemoglobin, our T state protein. And I wanted to take the R state protein, our oxygenated hemoglobin, and overlay these two images. It's really kind of tough to see because there's a lot going on there. But what this image on this deoxygenated hemoglobin is trying to illustrate to us is that we have a couple of select amino acids. Now there's a amino acids 38, 41, 97, 44. Those amino acids are highlighted, and then they're actually also highlighted in the oxygenated hemoglobin. So the same residues are highlighted and used kind of as a basis for comparison. Now I'm going to take the image that I selected and copied, and I'm going to overlay it. And one of the things that's, oh man, it's too tough to see. There we go. Okay, so we've got this residue number 38, which I'm going to circle in black, and our deoxygenated hemoglobin. So when hemoglobin has not bound to any oxygen, that's where that's where that protein, or that's where that amino acid is. Now I'm going to take this other image and overlay the common axis. And then I'm going to actually, here, I'm going to draw a black circle around this other image. So I've got two black circles highlighting the same amino acid. Okay. Oh, darn it. I can do this. Okay, so there we go. I'm going to group these things. Group. Looks like a donut. Oh, come on, man. I grouped them. Group. Okay, so so I'm going to find my central axis. Okay, here, this is exactly what I wanted to show. Now, that one amino acid has moved. We have this common axis in the center, just so you can see, okay, these two images are overlaid from one another. Now, that might not look like very much, that movement from the first position to the next position. But I've always thought about these changes in protein structure as similar to, I don't know if anyone's ever watched any sort of like show where they do any sort of cosmetic surgery. I remember watching one where someone was talking about getting a facelift, and the surgeon was saying that the movements that they make they'll never, whenever they're doing a facelift, they're never going to move anything more than like 8 millimeters. So let's put that into context. 8 millimeters is less than 1 centimeter, because 10 millimeters is 1 centimeter. So we're talking about less than a centimeter. And also for context, there's 30 centimeters in 1 foot. So we're talking about a very, very, very small movement. I don't have a ruler anywhere near me, but I hope you can get the point. And where I like to go with that is when those movements are made, someone's appearance has drastically changed, or it has changed considerably. I'd like to use that as kind of a parallel, because we're talking about a protein where a single amino acid moves a little bit. That one amino acid moving a little bit might seem kind of like innocuous, but when we have lots of amino acids moving a similar distance, well then, or moving similar distances, then that's lots of movements leading to a protein that looks considerably different. Now, as those proteins, or as these different amino acids move in different distances, you're going to lead to something that overall structurally is pretty massively different. So these are minor movements. So this change is very minor. These changes are minor, but there's an aggregation, or a reaches a fever pitch where this protein that didn't bind oxygen now has a very high affinity for oxygen. But we're going to get more into these different states, the T state and the R state, in a little while. So when we look at the structure of hemoglobin, because that's critical for understanding its ability to bind oxygen, it's sometimes, and I mentioned this a few days ago, or I mentioned this the other day, that sometimes it is referred to or is viewed as a dimer of dimers. So mammalian hemoglobin is an alpha-2 beta-2 tetramer. So that means it's got an alpha, or 2 alpha subunits, 2 beta subunits. So its quaternary structure is a dimer of dimers. So there's an alpha beta dimer and another alpha beta dimer making up that tetramer. So the alpha beta dimers associate through hydrophobic interactions and ionic interactions and hydrogen bonding. The dimer of those 2 alpha beta dimers. So think about it as you've got an alpha part and a beta part that come together to make dimer number 1. And then you've got another alpha part and another beta part that come together to make dimer number 2. Those 2 dimers come together to make that tetramer. Now, the dimer of alpha beta dimers associate through ionic interactions and hydrogen bonds. What's worth noting about this is, okay, so the 2 dimers, the tetramer, is basically stabilized through ionic interactions and hydrogen bonds. The individual dimers, on the other hand, well, they have hydrophobic interactions. So this detail right here is very important. Now, pH changes will affect the dimer-dimer interactions, but not the 2 individual dimers. So basically, you've got something that looks like this, alpha, beta, and then we've got alpha, beta. So if you change the pH, it goes up or down, whatever. What's going to happen, or what can happen, is you'll end up with this right here and this right here. This alpha beta and this alpha beta. But these 2 subunits, because of the fact that they're stabilized through hydrophobic interactions, those are going to remain intact. I want you to understand and appreciate that detail. Now, this provides a little bit more context and a little bit more detail for some of the interactions that are taking place within the T state. The T state, the deoxygenated form, is stabilized by a series of ion pairs that lie at the intersection between the alpha beta protomers. So those two components that come together to make those bigger subunits, or to make the complex as a whole. Now, this is showing us like the specific amino acids, arginine and aspartic acid interact, and arginine and aspartic acid on this combination interact. The N termini and the C termini interact, N termini, C termini, C termini and lysine, lysine and C termini. That's detail that I'm not too focused on you knowing about, but this is just illustrating that we've got all these different R group interactions as well as N and C termini interactions that are going to stabilize those ion pairs for the T state. I want you to know the T state is stabilized by ion pairs. The specific ion pairs, I don't want you to worry too much about that. Now, this model right here, I think I can go over about 3 more slides. Let's see. This one. Yep, 1, 2, 3, 4. Yeah, about 4 more slides. Okay, so we transition from the T state to the R state, the deoxygenated T state to the oxygenated R state. Now, I want you to recognize between these two proteins, the T state and the R state. If you look at the T state, I always like to, draw a figure or something like that. Let's go ahead and insert a, go ahead and, nope, cancel. That's not what I'm looking for. Insert a shape. Let's go with a box. There we go. Got a box there. I'm going to adjust the angle a little bit. I think it's pretty safe to say that that box kind of frames what we're looking at with respect to that central cavity there. Okay, so that big central cavity in the T state of our protein, when we have all these different movements in the T state, and we end up with an R state, now all of a sudden that central cavity is shrunk down considerably. And that's worth noting because this is a very tightly and highly regulated protein. There are even some amino acids, this histidine here, that's interacting within this tetramer in that central cavity. That, well, heck, that histidine that we're highlighting, it's moved from here to the center. So there's pretty dramatic changes that take place when this protein transitions from the T state to the R state. Now, oxygen binding of that protein, as I've mentioned, causes a stark conformational change. Oxygen binding causes a conformational change to occur at the heme molecule. Okay, so now depicted in blue here, we are seeing oxygen not bound. And so let's look at our helix. The helix is up here, it's at this angle, and then let's look at our heme ring. Our heme ring has kind of it's almost like an inverted V. Okay, so that's important because what's going to happen, or what we're going to notice, is that heme ring and everything in blue is going to undergo some changes when oxygen binds. Namely, that iron is outside of the heme plane. Okay, so what's going to happen is when oxygen binds to the iron, it's going to basically pull iron downward. When it pulls iron downward, that means that these rings of our heme molecule, it's going to flatten out. So if you think about it as they're basically going to go from this inverted V to a flat shape. Now, what that's also going to do is it's going to cause this helix, this F helix, is going to shift downward. So the binding of oxygen kind of pulls down that alpha helix. And this is all because iron pulls that histidine F8 about 0.6 angstroms. So it pulls that downward. that entire F helix moves when the oxygen binds. And that's going to be one of the things that leads to the conformational change from the T state to the R state. So oxygenation causes that F helix of one alpha beta dimer to shift relative to the C termini of the opposite alpha beta dimer. So here's what we're looking at. We're looking at this F helix that was close in proximity to one part of the other dimer. Now it has a different position. O2 binding causes a conformational change or a shape change in the subunit. As more O2 molecules bind, hemoglobin transitions from the low affinity T state to the high affinity R state. So that transition is going to be resulting from what's known as cooperative binding. The observed oxygen binding curve depicted here. Let's go ahead and change color. I'm going to here has a sigmoidal shape. Now, this is only going to be because of hemoglobin, or because hemoglobin is a multi-subunit protein. So this change results from hemoglobin being a multi-subunit protein. Now, this phenomenon is known as cooperativity. And to illustrate cooperativity, we've got this graph right here, this model on the right-hand side of this page. Hemoglobin, depicted right here, has no oxygens bound. And this form of hemoglobin has a very low affinity for oxygen. Hemoglobin, when the concentration is high enough, will bind to one oxygen molecule. And what ends up happening is this hemoglobin with one oxygen molecule has a slightly higher affinity for oxygen than the hemoglobin with no oxygen bound. Hemoglobin with two oxygen bound has a higher affinity than hemoglobin with one oxygen bound than hemoglobin with no oxygens bound. We're going to get that third oxygen, and ultimately we have our fourth oxygen that binds. So as hemoglobin binds more and more oxygens, it wants oxygen a lot more. Now, for what it's worth, I always think about this as like, I think that there's one parallel that I always like to draw is like a junior high dance or something like that, or going to a wedding. No one really, or going to a wedding and a dance floor. Nobody wants to really be the first person to break the ice and be the first person on the dance floor. Or, I mean, I don't mind doing it. I like doing it. But some people have a hesitation about doing it. And so they don't want to be the first one to like break that seal. But when they see other people on the dance floor, then they're like, ah, it's safe. I'll go. So hemoglobin is the protein, or hemoglobin with no oxygen bound is like that empty dance floor. But as soon as you get one oxygen to bind to it, you have monooxygenated hemoglobin, then all of a sudden the second oxygen is like, well, I guess it's not such a bad idea. I'll bind to oxygen. And then the third oxygen is like, well, I mean, if two oxygens are going to bind, it's a pretty good idea, I think. And then finally, whenever this oxygen, or this hemoglobin is fully saturated with oxygen, all of the oxygens are like, I wanted to be here the whole time. I really love it. So positive cooperativity is basically the affinity increases for oxygen as more oxygen bind. It's kind of like the rich get richer. The oxygenated hemoglobin wants oxygen, or holds on to oxygen with a greater affinity than the deoxygenated form. So what that's going to do is that's going to make the oxygen binding curve from hemoglobin have a different shape than that of myoglobin. Here we've got myoglobins. And with myoglobins, it goes up pretty fast, but then it plateaus. With hemoglobins, it doesn't go up very fast. And then it kind of plateaus. It does the same thing, but it doesn't go up very fast. In order to illustrate these differences in, or these differences in binding laws, we have to kind of adjust the graph, or adjust the equation accordingly. So that's actually where I'm going to stop we'll pick this up again, or we'll start with this cooperativity in the hill plot, in the hill equation on Tuesday. At any rate, I hope this is helpful. If you have any questions, let me know. Other than that, have a good one.